The system has spin rotational invariance, and it has total number of electrons in each valley is a good quantum number, but system is still almost independent of valley as well. So there's almost SU4 invariance in spin valley space, and that symmetry is broken.
That's a continuous symmetry.
That's for spin, it's truly continuous. For the valley degree of freedom, almost continuous. So, so the calculations I showed you, just to be specific, are basically time-dependent mean field calculations. So, when we knew these calculations, when we did these calculations, we knew we should get a gapless Goldstone mode for the broken spin degree of freedom. One of the things we were interested in was how big would the gap be for the valley degree of freedom. We expected a valley mode below the continuum. That came out to be 1 eV. The gap in the system, quasi-particle gap, is about 10 MeV. What I was unsure about when we did the calculations is whether spin waves, for example, would be below the continuum throughout the Brouwer zone. Like there's, when the spin waves exist for every Q in momentum space, it's like a local spin model, right? So we have a local spin model, local valley model. So there's a spin valley degree of freedom at each site. And the surprising thing is that there are two flat bands always. There's a flat valence band and a flat conduction band. That's what's continuously being remixed by interaction effects when the Fermi surface shapes change. And so it turned out that valley, or that band, if you like, or orbital excitation also exists locally. So at least in these calculations, that there's a branch of low energy excitations that maps to an object 1 per Moire period that has an SU8 degree of freedom in spin, cross, valley, cross, orbital, if you like. So,
and you suspect these connected modes might have something to do with bearing?
Yeah, for example, especially the interorbital mode, because let's talk about spin, for example. So, with the spin degree of freedom, let's say it's spin polarized. So that means all of the bands that have different spins are separated by 10 millielectron volts or so. Lost my train of thought. Yeah. So okay, thank you. When a quasi-particle interacts with the spin wave, it scatters the quasi-particle from one spin to another. So it will not scatter it within let's say, majority spin. The spin polarized Fermi surface is not going to scatter off spin waves within that band. But with these orbital modes, there is scattering within the bands due to these low energy orbital degree, orbital collective modes.
So that would be an internal.
Maybe that requires a longer answer with a piece of paper, but that's roughly it.
Superconductivity, as you choose where the energy of these modes is low.
Yeah, okay. The question was, is there a coincidence between where superconductivity is observed experimentally and where these modes have low energy? Certainly these modes have not been seen experimentally yet. That would be, they should be visible in some kinds of infrared optical spectroscopy. So I think that's an important type of experiment. Superconductivity is seen over, a broad range of twist angles from 1.05 to 1.25. That's roughly where we think that, where these very low energy collective modes exist. So theoretically, I think the answer is it's at least plausible that these modes exist where superconductivity is seen. Another thing that is connected to what Philip has been emphasizing, it could turn out in the fullness of time that we understand that superconductivity in these twisted structures occurs only in twisted bilayer graphene. And that means it has something to do with these magic angle flat bands. And what's special about these magic angle flat bands and what's connected to this, the way we're trying to improve our understanding of why these interband collective excitations should have a low energy. And we think it might be connected to the chiral property of the flat bands that's been emphasized. Some of you may know in work by Aspen, which is only an approximate thing, but anyway, we think that the fact that these modes, collective modes, have this low energy might be connected with those properties, and they're special to magic angle twisted bilayer graphene. So that's another way in which perhaps the existence of this unusual type of collective mode and the existence of superconductivity go together.
Sorry, I thought the collective modes were nearly Goldstone modes.
No, not necessarily. So,
Again, can you repeat the question?
yes, I thought the collective modes were nearly Goldstone. Okay. So there is the spin mode, is a Goldstone mode. It has zero energy at k equals 0. We expected the Valley mode to have a low energy at k equals 0, especially because we know that the system is only weakly dependent on the Valley degree of freedom. And so breaking that symmetry we thought would lead to a low energy collective mode. So the Valley mode ends up having an energy of about 1 million electron volt, well below the particle hole excitation continuum. The surprising thing is that there's another collective mode, one that actually whose fluctuations couple to a partially filled band, which has, let's say, definite spin and valid. That also has a long period, also around 1 million electron volt.
So that you can't interpret that in terms of Goldstone as a Goldstone mode of some sort.
None that we know, anyway. So the system might have some approximate symmetry that we haven't recognized.
But the reason I ask is that these broken symmetries are supposed to be characteristic of the insulator, right?
Yeah.
Right. Whereas superconductivity is definitively outside of those. So a Goldstone softness would not be a diagnosis, would not be a prescription for superconductivity.
And there are other reasons that quasi-particles within a partially occupied band don't couple to these collective modes generally. But Alan,
I'm sorry, can you also move this way, because I think people out there.
Yeah, the mic is actually here, and we got some participants.
Sam was asking some good questions about what collective modes can give superconductivity, and the true Goldstone modes don't couple to states within the same band, at least in a simple picture. So
there was, okay, so we take 2 last quick questions, will we?
You were also linking.
So this is obviously totally speculation at this point. I'm just being very open about the ideas I'm working on.
You're just being recorded.
Yeah. That's okay.
So you're also linking both.
Yeah.
The
Yeah, absolutely. So
these would come together. So phenomenologically,
phenomenologically, they do come together. The T-linear resistivity is seen over a range of twist angles, the same range of twist angles, more or less, where we see superconductivity, the same, although we haven't explored it theoretically thoroughly over this entire range of twist angles. It's the same range of twist angles where we expect these.
So it's T-linear resistivity seen in other non-graphene.
Philip?
You unmute your audio.
Did you hear the question?
I didn't hear the questions. If you can repeat, that would be
You
helpful.
need to unmute yourself.
I did unmute,
There we go. There you go. All right. Good. Thank you, Amanda.
but I didn't hear the questions well.
Yeah, so can you hear me?
Yes.
Okay, is T linear resistivity seen in double bilayer graphene or in TNT?
Okay, so I think the experimentally, I think it's kind of limited in kind of both sides, the low temperature as well as high temperature side. So I'm not sure whether I can say that with confidence that we are seeing the T linear type of the behavior. I think there is a certain regimes is linear, but whether it's easy, whether do I have the confidence in terms of this the saying that this T linearity is really obvious, because you see that the higher band is not too far from this flat band. So as soon as you get into the 30 or 40 Kelvin, you start to see the effect coming from the higher populating higher band, right? So all this experimental the arguments, whether you see the T linear or T nonlinear, this is a kind of based on a relatively small energy scale, a small kind of range of the temperature. So I think in that regard, I don't say that I have confidence to say that I've seen the T linearity in the double bilayer, right? I don't know whether that is that the answer that you guys want?
Yes, I'll do it.
Yeah.
I had a quick question for Philip, just following up on the superconductivity or not.
Yeah.
If one imagines that in some systems it's not superconductivity, do you have a picture that you're forming, whether it's from heterogeneous conduction that has some real spatial structure?
I think that for us that if it is not the superconductivity, another possibility is basically the spin mediated spin fluctuations mediate the scattering events. So basically somehow in higher temperature we have a lot of the spin mediate the scattering events for the electrons, such that we have the higher resistance. But as you go to the lower temperature, if the spin order is happening, and then basically suppress those kind of fluctuations and suppress the scattering events. So that could be kind of possibility, and those kind of effect has been seen in some of the magnets. So I think that could be one possibility. But we are seeing the rather steep the resistance decreases. So that's I don't know whether how quantitatively that picture can be explained. The other, of course, possibility is, you know, that electron phonon interaction is a rather strange, is in that narrow band system, and then we are crossing that kind of this narrow band. There are a lot of the low temperature the phonon mode hanging around in the flat band region, flat phonon band region. So could be one can cook up something like this weird electron phonon scattering that produce sharp drops of the resistance around the certain temperature ranges. But I've been seeing that this, yeah.
Okay. Thank you, Philip. Thank you, Alan.